Now that we've looked at polar coordinates and how to graph polar points in polar graphs, let's go ahead and talk about the polar coordinates and how calculus is involved. Now, one of the first things that we learned about calculus or in calculus was trying to find derivatives and slopes of tangent lines. So let's go ahead and pick up there as well with polar coordinates. Now, when we talk about slopes of tangent lines, we are talking about derivatives. Remember, the slope of the tangent line gives us the tangent line gives us the slope of the tangent line at any point along a graph. Kind of gives us a lot of information about whether the function is increasing or decreasing. Now, what we're used to working with in the rectangular coordinate system is if we have some function y equal f of x, then we end up with the derivative of y is just the derivative of f of x. However, when we're working with polar coordinates, it doesn't quite work like that. So if we have r equal f theta, this does not imply that r prime is equal to f prime theta, meaning I just don't take the derivative with respect to theta. Now, the reason this is that the slope of the tangent line, remember slope is change in y over change in x. Change in y over change in x. Now, change in y is change in the vertical. Change in x is the change in the horizontal. Okay, so that's what we have going on here. Now, when we talk about polar coordinates, we're not necessarily talking about horizontal and vertical components. We're talking about radius and angular components. So we have to change what we do here then. So to find the slope of the tangent line in a polar equation, we have to kind of go back and work with parametric equations basically. So the first step that we would look at would be to rewrite r equal f theta. And this is basically my equation of my polar equation, I should say. And so we want to rewrite this in parametric form. So to get back to parametric form, of course, we know x is equal to r cosine of theta and y is equal to r sine of theta. But we know from right up here that r is equal to f of theta. So we end up with x equal f of theta cosine theta. And here y is equal to f of theta sine of theta. So that's kind of where we start. Now from here, I can start taking derivatives. So if we want to find out what dy dx is, my derivative, this would equal to dy d theta over dx d theta. So if we talk about dy d theta, kind of over right in here, I have to use the product rule. So the product rule would be the first function, which is f of theta, times the derivative of the sine of theta, which is cosine of theta, plus the second function, which is the sine of theta, times the derivative of f prime of theta. Now dx d theta, I'm going to use a product rule as well. So I have the first, the derivative of the cosine is a negative sine, so first times the derivative of the second plus the second times the derivative of f theta is f prime of theta. So let's simplify this just a little bit. Now there's several ways that you can rewrite this. So this is basically my derivative, which of course is the slope. Looks like I could rewrite this as, let's rewrite this as f theta cosine theta plus f prime of theta sine theta. And this is definitely one that you'd want to have on your note card for the exam, unless you feel like deriving it every time. And then I'm going to move the positive out front, so I'm going to call this f prime of theta cosine of theta minus f of theta sine of theta. Okay, so we have this all written out, and again, there's several different ways that we could rewrite this, meaning I could switch the terms in the numerator. In the denominator, it could factor out a negative or something like that as well. But this is going to be a very important equation that you'll definitely want to know. Okay, now from here, we should be able to find the slope. Now remember, m represents slope. So let's go ahead and start looking at some problems. Now on a test or your handwritten homework, I will usually provide graphs if needed. If we're trying to find, let's say, slopes of tangent lines or trying to find horizontal or vertical tangent lines, just to kind of give you a context for the problem. I don't expect that you'll be able to graph a lot of polar graphs. The basic ones that we looked at in that last lesson I would expect, but anything beyond that I would probably provide. Okay, so for this problem, let's go ahead and find the slope of the tangent line. So right away we know we're talking about derivative. So find the slope of the tangent line to the curve, to the polar curve, r equal 2 sine theta. And we need to have a particular point, so we'll say at the point. And again, this is a polar point, 1 pi over 6. Okay, so all of this is polar. So to get started, let's go ahead and realize that f of theta is equal to r. Is equal to 2 sine of theta. Okay, so now we know from our formula up above that dy dx, which of course is my slope, we'll have my formula, f of theta cosine of theta plus f prime of theta sine of theta, f prime of theta cosine of theta minus f of theta sine of theta. So that's my formula. Now I have to actually do the steps of the formula. So this then for my problem would be dy dx, and of course that's equal to the slope, would be f of theta. Well, f of theta is equal to 2 sine of theta. Now for here, I just have my cosine theta now. So here's f of theta cosine of theta plus the derivative of f of theta. The derivative of 2 sine theta is 2 cosine of theta. And then of course my other sine of theta comes from right here. Now of course we have to simplify the heck out of these things when we're done, but for now let's just go ahead and focus on the derivative part. Okay, denominator, I need f prime of theta, which is 2 cosine of theta. And then my cosine of theta comes from here. Minus f of theta, which is 2 sine of theta, times the sine of theta, which comes from your formula. Okay, so let's go ahead and simplify this. So again, dy dx, and again this is my slope. So simplifying, I have 2 sine theta cosine theta, and here's another 2 sine theta cosine theta, so I have 4 sine theta cosine of theta. Now my denominator, it looks like I have 2 cosine squared minus 2 sine squared, so I could factor out a 2, and I'd be left with 2 cosine squared theta minus sine squared theta. And then of course I can reduce, 2 goes into 4 twice. So I'm left with sine of theta cosine of theta over cosine squared of theta minus sine squared of theta. Now one thing that I notice here is cosine squared minus sine squared is a Pythagorean identity. Whoops, and I have a 2 right here. Sorry, but I don't want to forget that. So I have 2 sine theta cosine theta over cosine squared minus sine squared. Now cosine squared minus sine squared is a Pythagorean identity. I think it's actually a half angle identity. I think it's cosine of 2 theta or something similar. So if you wanted to, we could go back and delve into these and try and rewrite these, but I'm just going to leave this and this simplified form, because if you notice, all of my angles are just good old thetas. They're not double angles, which are harder to work with. So now that I have this simplified, I need to evaluate this at, and again, all my values here are thetas, so I'm going to evaluate this at theta equal. Let's go back at my original problem. So pi over 6, because this was r and this was theta, so theta is pi over 6. So this is 2 sine pi over 6, cosine pi over 6, over cosine squared pi over 6, minus sine squared pi over 6. Okay, rewriting, sine of pi over 6 is a half, cosine of pi over 6 is square root of 3 over 2. Cosine pi over 6 is square root of 3 over 2, and that of course is quantity squared, minus 1/2 quantity squared. 2's cancel, and I'm left with square root of 3 over 2 in my numerator. My denominator, I'll have 3/4 minus 1/4 is 2/4, or a half. Now remember, when you divide by a fraction, you multiply by the reciprocal. So this 2 flips, and the 2's cancel, and I'm left with root 3 as my slope at the ordered pair 1 pi over 6. So there's my big information, to be able to find that value of root 3. Now one other thing I'd like to be able to do is to actually graph this and have a look at what's going on. So let's just go ahead and graph r equal 2 sine theta. So there would be my circle if it was just r equal 2 sine, and then of course my variable here is theta. So this is what my graph looks like. This is a circle. This is a circle with a center at 0, 1, and it looks like it has a radius of 1 as well. So if you wanted to convert this to a rectangular coordinate system or a Cartesian coordinate system, that would be pretty simple to do. So let's go ahead and pull this graph into our lecture and see if any of this makes sense. So what we were trying to do is we were trying to find the slope of the tangent line at 1 pi over 6. So if we looked for 1 pi over 6, this 1 right here is that circle, and pi over 6, we could assume probably it's that first line. Let's go ahead and pop that open and have a look. Okay, so pi over 6 is right here, so it would be that second line. So if we were to graph that point, it would be 1 pi over 6. It would be right here. So basically I'm trying to find the slope of the tangent line at this point. So this is the line, and then the slope of this line is the square root of 3. So that's what I found out. Now a couple of other interesting things that I would like to know about are if this graph has any horizontal tangent lines, which I believe it does up here and down here. And then I also like to look for vertical tangent lines, and it seems like we have vertical here and here, if I can find out where those are. So let's go ahead and do that next. So same graph, let's go ahead and determine any horizontal tangent lines to start with, and then we'll find vertical. Actually, before we do that, let's talk about this line real quick. Usually in our other calculuses that we looked at besides the polar coordinates, we'd always want to find the equation of this line. It's really difficult to find the particular equation of this line, because if you notice, this is not coming out of the origin at any point. So trying to find this equation would be pretty difficult. So, don't focus so much on that, just focus on the slope. We could, however, find the equation of the tangent line as it goes through the origin, because we can see that this is a flat line. So this is a line where theta would equal 0, because my degrees, or my radians, are flat. They're going to be 0. And of course the radius is arbitrary then, and so here I'd have theta equals 0. And that's going to kind of lead us into looking at horizontal and vertical tangent lines. Let's start with horizontal tangent lines. Now again, by looking at our picture up above our graph, it appears to me we have horizontal lines, tangent lines here, so that would be at 0, and then up here as well, which is also at 0 in terms of my radians, but then we'll have to worry about those points. So let's go ahead and be pretty specific about this. Find the points on the interval from negative pi to positive pi at which the cardioid let's go ahead and do a new graph on this one. Even though I can see where I have my horizontal and vertical tangent lines on this graph, let's go ahead and look at a new graph just so we can kind of get used to a few new graphs. So the cardioid I want to look at is going to be r equal f theta equals 1 minus cosine theta. So find the points at which the cardioid has vertical or horizontal tangent lines. So we know we need that formula for the derivative, but before we do that, I would really like to look at what this graph is like. So let's go ahead and graph r equal f of theta equals 1 minus cosine theta. So r equals 1 minus cosine of theta. Okay, so here's my cardioid. This one is on its side. Let's go ahead and grab this and put it in our lecture. Might have to refer back to this, so I'm going to leave it open. So as we look at this picture, it definitely appears that there's some horizontal tangent lines and some vertical tangent lines as well. So if I were to look at these in terms of horizontal tangent lines, looks like to me there's a horizontal tangent line here. I'll need to figure out, what's going on here in terms of where that occurs. Also a horizontal tangent line below to figure out where that happens. And there could be a horizontal tangent line here. I'm not sure. We'll have to check. And then, of course, vertical tangent lines is where my slope is undefined. It looks like it appears here and here. And again, something's going on here at the pole or the origin as well. We'll have to check that out. Let's go ahead and start with horizontal tangent lines. So first of all, we need to find the derivative. So we want to go ahead and find dy dx. And so we'll want our formula that we derived in our last, actually we did that right away before our last problem. So formula, and again there's several different ways to write it. So is equal to f prime theta sine theta plus f theta cosine theta all over f prime of theta cosine of theta minus f theta sine theta. So this is just the formula. I haven't done any of the work yet. So let's go ahead and look at my derivative, which of course is equal to the slope. That's equal to f prime of theta. So the derivative of 1 is 0. The derivative of a negative cosine is a positive sign. So this is going to be sine theta times sine theta. Now just as a quick review, this says to take the derivative of f of theta. F of theta is equal to 1 minus cosine of theta. The derivative of 1 is 0. The derivative of a negative cosine is a positive sign, so that comes in down here. Plus f of theta, which is 1 minus cosine of theta. And of course cosine theta comes from here. This is all over f prime of theta, which is 1 minus cosine of theta. Cosine theta comes from here. Plus f of theta. Actually, this is f prime of theta, so this is just going to be sine of theta. Got to keep better track of things here. That came from the derivative. Plus f of theta, which is 1 minus cosine of theta sine theta. Now we could leave this as is, but this would be really difficult to work with. So I'm going to go ahead and keep simplifying. So it looks like to me I have sine squared theta plus cosine theta minus cosine squared theta. My denominator, I have sine theta cosine theta plus sine theta minus sine theta cosine theta. And I think I dropped a negative somewhere here. So my negative should be right here. So if you notice, this was negative, and then I switched it to a positive, so this has to stay negative. So this would be a negative sign. This would be a plus sine theta cosine theta. Now the numerator, if you notice, is almost in terms of all cosines. We could rewrite this, and it'll make our lives a lot easier. If you remember the Pythagorean identity, sine squared plus cosine squared is 1, so sine squared is equal to 1 minus cosine theta. And again, that's just a quick little rewrite. So I have 1 minus cosine squared of theta plus cosine of theta minus cosine squared of theta. So my hope is we can start to simplify some of this. Sine theta cosine theta is 2 cosine theta, 2 sine theta cosine theta when I add those together. Minus sine of theta. Okay, so here I have a negative 2 cosine squared theta plus cosine of theta plus 1. Make sure you have everything right there. And in the denominator, if you notice, there's a sine theta that's common. So I'll just go ahead and pull it out this step. So I'll be left with 2 cosine theta minus 1. Now the numerator does factor. I could pull out a negative. And if I pull out that negative, in fact I'll do that here, 2 cosine squared theta minus cosine of theta minus 1. I could factor this into 2 cosine of theta, cosine of theta. Now I need a minus cosine of theta, so I think I'm going to need my minus 1 and my plus 1 right here. And that does factor then. Now it looks like it's really, really close to being able to be canceled, but not quite. So even though it looks tempting to cancel these, I can't quite do that. So we have our derivative, it's in simplified form. So now let's go ahead and talk about horizontal tangent lines. Okay, horizontal tangent lines occur when the slope is equal to 0. So basically what I need to do is I need to take my slope and figure out where it's equal to 0. So I will be good if the numerator equals 0. So this is the numerator equals 0, but I have to double check and make sure the denominator doesn't equal 0. Because if the denominator equals 0, I'd have 0 over 0, which is kind of a whole other problem. So the numerator equals 0. Check that the denominator doesn't equal 0 at any of these points that I find. Okay, so divide through by negative and end up with 2 cosine of theta plus 1 equals 0, and cosine of theta minus 1 equals 0. Cosine of theta equals negative 1/2. Cosine of theta is equal to 1. Now remember, my restrictions were negative pi to pi. So this is saying, where does the cosine equal negative 1/2? So what angle has a cosine of negative 1/2? Well, that's going to be in second and third quadrants, but it has to be between negative pi and pi, so I have to be careful about how I write that. So if I think about negative pi to pi, I'm starting here at negative pi. I'm moving in this direction. I'm ending at pi. So this is kind of where I need to focus in on and make sure my angles fit. So for here, cosine of theta is equal to a negative 1/2. That would be at a negative pi over 3. And so that'd be in my negative pi over 3 and negative 2 pi over 3. Actually, at negative pi over 3, that's not true, because negative pi over 3 is in the fourth quadrant, and I already said that cosine is negative, so I have to be in the second or third quadrant. So that would be at negative 2 pi over 3, would come from here, and then at, so here would be pi over 3, and a positive 2 pi over 3. And then where does cosine of theta equal 1? Cosine of theta equals 1 at 0. So basically, this is where I think I have horizontal tangent lines, but I have to double check. And the reason I need to double check is to be sure that the denominator does not equal 0 at any of these points. So note, denominator does not equal 0 at, so I'm just looking right up here, I'm just checking right here. There shouldn't be anything going on with 2 pi over 3 or negative 2 pi over 3. That looks good. And if I plug in theta equals 0, sine of 0 is 0. Oh dear, so I do have a problem. So the denominator does not equal 0 at, okay, plus or minus 2 pi over 3. I have a problem here. The denominator equals 0 at this point. So let's run back up here and check and see what's going on. So that's saying at this point, remember what we're looking at here is theta. So if theta equals 0, cosine of 0 is 1, 1 minus 1 is 0. So it's at this point we're saying we have a problem. We have to figure out what's going on. It looks like it could be horizontal. It looks like it could be vertical. It's kind of a sharp point, so it's kind of hard to determine there. Okay, so let's go ahead and look at those two horizontal tangent lines, and these do make sense. It looks like there is 2 of them, and then we kind of have to work from there. So I'm guessing that would be my 2 pi over 3, and down here would be that negative 2 pi over 3 line where that's hitting. Should probably be a little bit closer right about here. Okay, so now let's go ahead and look at vertical tangent lines. Now vertical tangent lines occur when the denominator equals 0. And then again, we have to check just like we did up here, and we already know we're going to have a problem right there. Check that the numerator doesn't equal 0 at those same points. Because if this is the case, that would be 0 over 0, which is indeterminate, and then indeterminate form would be a whole nother deal. It wouldn't give us a proper horizontal slope or vertical slope, either one. Okay, so as I'm looking for these vertical tangent lines, I take that denominator, which was sine theta times 2 cosine theta minus 1. And I set it equal to 0. So my first one would be sine theta equals 0. Second equation that I'm looking at is 2 cosine theta minus 1 equals 0. So this would be cosine of theta equals 1/2. Sine theta equals 0. Now where does sine theta equal 0? Now remember, I'm going from negative pi to positive pi here. So I think that this would happen at negative pi and pi. That's where my sine would be equal to 0. And then where does the cosine equal 1/2? Well, that would be quadrant 4 or 1. So it would be negative pi over 3, positive pi over 3. So I have 4 values to check here. Now my numerator, if you will recall, is right here. So as I plug in pi, cosine of pi, 2, 1, cosine of pi, 1 minus 1 is 0. So it looks like I could have some conflicts here. But remember, my numerator can't be 0, so let's double check. So I'm going to check pi first. Cosine of pi is negative 1. So this would be a negative 2 plus 1 is a negative 1, so that's good. Cosine pi is negative 1. Negative 1 minus 1 is negative 2, so that's good. Let's go ahead and pi, I'll get the exact same thing. And then let's go ahead and look at negative pi over 3 and positive pi over 3. There shouldn't be any problems. So I have vertical tangent lines at negative pi and positive pi, negative pi over 3 and positive pi over 3. So let's have a look. So negative pi and positive pi. So here, if we look across to here for our radians, this would be a negative pi and a positive pi, because as I move in this direction it would be a negative pi, in this direction it would be a positive pi. And then it looks like I have negative pi over 3 and positive pi over 3. So this would be my positive pi over 3, and this would be my negative pi over 3. And that totally makes sense then. I have those vertical asymptotes there. Now it looks like we've checked everything except we had that weird case when theta was 0. Remember, I had the denominator was equal to 0 and the numerator equals 0 in this case. So I guess we should better summarize some of this. So here I have horizontal tangent lines at theta equal plus or minus 2 pi over 3. And then here I have vertical tangent lines at theta equal plus or minus pi, which is actually the same point, and plus or minus pi over 3. So that's kind of summarizing everything. Now I had this strange case, what about when theta was equal to 0? Okay, well, if we think about theta equals 0, if you remember, I had 0 over 0, which is indeterminate L'Hopital's, and so I need to take a derivative. Because remember, I'm thinking about this in terms of a limit. Because if I plug 0 directly in, I get 0 over 0, which is an indeterminate L'Hopital's form. So let's go ahead and think about this as a limit as theta approaches 0. And my numerator, I guess to back up, we could go ahead and plug in first, just to make things a little bit easier. So this would be a negative quantity 2 cosine of theta plus 1 times cosine of theta minus 1. And again, I'm just copying this directly from the original derivative. So this is sine theta times 2 cosine of theta minus 1. Okay, so if I plug 0 directly in, I get 0 over 0, which is indeterminate L'Hopital's. And L'Hopital says, okay, take the derivative of the numerator and the derivative of the denominator. So I'm going to go ahead and let you take the derivatives here. You end up with 4 cosine theta sine theta. Gonna have to use some product rule with that. Plus sine theta. Now the denominator is quite a different deal. It's going to be another product rule, so it'd be sine theta times a negative 2 sine theta plus 2 cosine theta minus 1 times cosine of theta. Now if I take my limit here, I end up with 0 over 1, which is just 0. So what this says then is the slope of the tangent line is 0 at the ordered pair at theta equals 0. So at 0, 0 at the pole. So if we come back up here and look at our graph, way back up here, right here, that's basically saying I have a horizontal tangent line right there. Before, when I was working with this piece, I kind of came up with this indeterminate form, and so I couldn't really say at this point that I had a horizontal tangent line, but after a little bit more work, I can kind of come in here and show that I do have a horizontal tangent line. Okay, so we've kind of gone over quite a bit just with derivatives, but of course there's all sorts of other things that we learned in calculus that we can do with a graph. And one of those things is to find the area of regions bounded by curves. So we won't just look at any curves here. Let's go ahead and find the area of the regions bounded by polar curves. Now things change a little bit here as well. Now this goes into Riemann sums and that whole idea about the limit, number of rectangles approaches infinity, but instead of rectangles here we're going to be looking at sectors. Now because we've already looked at Riemann sums before, I'm not going to focus in on how we derive this formula. I'm just going to make sure that we know how to use it. So we have some region R, and we'll do a curve sketch here. Let R be the region bounded by the graphs. And we'll have R equal f of theta and R equal g of theta. Now when we're talking about R, f of theta and g of theta, we also have to have another bounding region. So we need to kind of know, let's say, upper minus lower or right minus left, but remember these are sectors, not rectangles. So these are going to be squashed between theta equal alpha and theta equal beta. Now there also has to be a particular relationship between f and g. So this will apply where f and g are continuous, of course. Don't have any gaps in the graph. And g is between f and 0. So there's kind of the setup that we have before we can really do anything from here. Now we also are talking about the interval that we've already talked about here, alpha and the beta. So we have some sort of a fixed interval as well. So since we already have that above, I won't worry about it. So the area formula that we're going to be looking at will go from alpha to beta, and the formula is 1/2, and again this comes from Riemann sums. So we've already done Riemann sums back in Calc 1. So I'm not going to refocus in on how we derive this formula. We just need to kind of think about our upper squared minus our lower squared, because these are areas of sectors. Sectors are triangles, 1/2 kind of base times height if you want to think about it like that. There's a little more to it, but this is kind of your basic idea. Now the graph, and again we're talking about 0, it's kind of our lower bound here. Now this formula also applies to below the curve, but we kind of think about it as above the curve to define and derive the equation. So we have some curve over here, we have some other curve over here, and then we have these alpha and beta lines. So we'll say our upper is beta, and our lower is alpha, and our curve here is r equal f theta, and our curve down here is r equal g theta. So if we look at where everything is bounded at, we're trying to find this region right here. So what I would do is I would take this and I'd split it up in these itty bitty sectors, and I'd find the area of each small sector, and then of course as the number of sectors gets larger and larger, I get a better and better estimate. So that's kind of what my idea is behind here. So now that we have everything set up, let's go ahead and actually do a problem. Now some of these are computationally heavy problems, but that's okay. You can run through most of these. I'm not going to throw in numbers that are huge, but again, they can get kind of long. So to get started, let's go ahead and find the area of a simple shape. Let's do a four-leafed rose. And this rose will be r equal f theta equals 2 cosine 2 theta. Now a lot of times it's good to use symmetry. So let's go ahead and look at a graph of r equal 2 cosine 2 theta. So r equal 2 cosine 2 theta. So there's our rose. Let's go ahead and pop this into the graph or into the lecture. Now if I could just find the area of one of these petals, that would probably be easier. And then once I find the area of one petal, because it's symmetric and all the petals have the same area, I would just multiply by 4 to get my overall area. So I think the petal that I want to kind of look at then, I don't even want to do a full petal. I think I just want to do this bit right here. And the reason I want to just do this little bit is I don't have to worry about then this lower piece. I can just look at finding the area of this and then multiplying by 8 in this case. So let's go ahead and set up our integral. There's going to be an 8 out front, and the reason there's an 8 out front is I have 1, 2, 3, 4, 5, 6, 7, 8 of these similar regions. And this is going to go, we're not sure where this is going to go from yet. We'll figure that out in a minute. But I know I have a half here, and the half would be my function 2 cosine of 2 theta. I don't have two curves, I just have the one, quantity squared d theta. So when I look at these triangles, these wedges I guess that we want to look at, here would be a wedge out here. These wedges will come down here from 0 up to whatever this point is. So this point is pi over 4. It bisects the quadrant. Now if you wanted to try and figure out, kind of where that was happening, you could try and take the leaves, convert them if you wanted to, and then find those points of intersection. But this one's pretty easy to look at because it bisects the quadrant, and I can come up with that because of symmetry. So this is going to go from 0 to pi over 4. So now we get to remember some integration skills. So half of 8 is 4, so I can pull that out front. 2 squared is 4. 4 cosine squared of 2 theta d theta. Okay, 4 times 4 is 16, so I'll go ahead and pull that 16 out front. Now, if you'll recall, the way I integrate cosine squared of 2 theta is I use a half angle identity. Cosine squared of 2 theta is equal to 1 plus cosine of 4 theta all over 2. 16 halves is 8, so I can keep pulling out those coefficients. So I'm 8, 1 plus the cosine of 4 theta d theta. And this is from 0 to pi over 4. Okay, so I think we're ready to integrate finally. The integral of 1 d theta is theta. Now to integrate here, u would be equal to 4 theta, du would equal to 4 d theta. So I'd have to multiply by a 4 on the inside, compensate with a 1/4 on the outside. So this looks like 1/4 cosine of u du. So that's 1/4. The integral of cosine is sine of u, but u is equal to 4 theta in this case. So simplifying, I have 8 theta plus 8/4 is 2 sine of 4 theta. And I'm going to evaluate from 0 to pi over 4. It's always upper minus lower. You know what? I think I have a coefficient off here. Where did this 4th come in from? So I pulled out the half. Yeah, I think that's right. We'll see how it falls out. So let's go ahead and plug in the pi over 4 first for my upper. So I have 8 pi over 4 plus 2 sine 4 pi over 4. That's my upper, minus my lower, which should be 8 times 0 plus 2 sine of 0. So this whole piece right here goes to 0. These cancel. The sine of pi is 0. So I'm just left with 8 pi over 4, which is 2 pi. So this would be units squared, because this is area. So that's 2 pi. Not just for this little wedge, but for the entire rows. So the entire area covered by the rows. So very doable. Those types of problems, I would expect that you could crunch through the numbers and handle those integration skills. Now, some of the more interesting problems occur when you have two curves involved and you have different shaded regions. Now again, if symmetry can come into play to make some of these easier, that would be great. So let's go ahead and do another problem where we're finding the area. Let's do inside the rows. And let's do r equal, let's do 10 sine 2 theta. So we should have 4 petals here, 10 sine 2 theta. And inside the circle, and the circle, let's do r equal 5. So this is a circle with the origin as the center with a radius of 5. Okay, so on a handwritten homework, you should be able to come up with these graphs on your own. But if this type of problem were to occur on a test, I would give you a graph. I'd show you the graph to kind of get you started. So we have r equal 10 sine 2 theta. So 10 sine, and then we have 2 theta. Okay, so there's one graph. Now my next graph is just r equal 5. So r equal 5. Now let's shrink this up just a little bit so we can see what's going on. So if I'm looking at the inside of both of them, I'm kind of looking at these little wedges right here. So they come up in this region. So let's go ahead and pop this into our graph, or into our lecture. And then we'll kind of try and go from there. Now a couple things I want to look at. I don't think that, yeah, I was going to say we might want to know what our angles are, but I think we can refer back to these if we want to. So again, if you need one of these on the test, I'll provide the curve. On a handwritten assignment, you should be able to come up with the curve using your graphing utility or using something like Desmos. Of course, we just found out in our earlier lecture that Desmos doesn't take care of everything. So the regions I'm looking for, because it's inside the rows and inside the circle, and it's and, so it has to be both, would be these regions right here. Now there's 4 of them. And because there's 4 of them and they're symmetric, I can just find the area of one and then remember to multiply by 4 at the end to find all of the enclosed area. So to get started here, I think we probably need to figure out where these are crossing. What are these points of intersection? Now it doesn't look all that complicated, but there are 3 regions here that I need to be concerned with. So let's go ahead and get started by first of all finding these points of intersection. So again, this is region 1, this is 2, 3, and 4. Okay, so if we're trying to find points of intersection, we know that r is equal to r, so I'd say 5 is equal to 10 sine 2 theta. Solving, I get sine of 2 theta is equal to 1/2. So where is the sine equal to 1/2? Well, it's probably going to be in my first and second quadrants. So that would be where 2 theta was equal to pi over 6 and where 2 theta would equal 5 pi over 6. So solving for theta, I get theta equal pi over 12 and theta equal 5 pi over 12. Okay, so that's kind of where we're starting at. Let's go ahead and find this pi over 12 and 5 pi over 12 on our graph. Okay, so as we're working through here, let's see if we can find that angle. They're not going to give us that angle, but we should be able to figure out what it is pretty easy. So if we zoom in on that, we know that this is pi over 12, so that totally works with what we thought. And then we need to know this one up here as well, so I'm going to zoom in on that just to verify. And we can see that this is equal to 5 pi over 12. I think I'm going to leave this blown up right now because we're going to want to come in and have a look at this curve in a moment. So this is pi over 12. And this one up here is 5 pi over 12. Okay. Now, I said there was 3 regions, so let's go ahead and figure out why there's 3 regions. And again, we're just working with that region 1 right now, and then we'll multiply by 4 when we're done. So the area is going to be equal to 0 to pi over 12, 1/2. Now let's go ahead and look at what we're trying to set up here. Now why did we say 0 to pi over 12? Because there's a tiny little wedge in here that goes from 0 to pi over 12 that's different than this area that has this sector and then this area over here. So my curve 0 to pi over 12 is this curve underneath right here. That's 10 sine 2 theta, quantity squared d theta. Okay, now I have another region from pi over 12 to 5 pi over 12. And that one's pretty easy to work with. That's just going to be this circle, which is just 5. So that's 5 quantity squared d theta. Then I have that tiny little wedge that goes from 5 pi over 12 all the way, and it comes down in here and it hits pi over 2. And that is going to be 1/2. That's that rose piece again, which would be 10 sine of 2 theta quantity squared d theta. So I have these 3 regions within that one region 1. And once I find this, then I'll just multiply by 4 for my final solution. So let's go ahead and work through this one. We haven't got to integrate in a while, so this is kind of fun. So 10 squared is 100, half of 100 is 50, so I'll go ahead and pull that 50 out. Sine squared of 2 theta d theta. This would be plus 25 halves integral pi over 12 to 5 pi over 12 d theta. 10 squared is 100, half of 100 is 50, so plus 50 5 pi over 12 to pi over 2 sine squared of 2 theta d theta. Now remember the half angle identity that we worked with up here earlier. 1 plus cosine of 4 theta over 2. We'll end up rewriting down here (1 minus cosine of 4 theta over 2 d theta. This is going to be 25 halves theta. I have a lot going on here, a lot to keep track of. This is going to be 50 integral 5 pi over 12 to pi over 2. The integral sine squared of 2 theta, I can't integrate that till I rewrite it as a half angle identity. 1 minus cosine of 4 theta all over 2 d theta. Okay, continuing to simplify. Half of 50 is 25. The integral of 1 d theta is theta. The integral here, u is equal to 4 theta. du is 4 d theta, so I'd multiply by a 4 on the inside, compensate with a 1/4 on the outside, and I'm left with minus 1/4 sine of 4 theta. Okay, now for this piece, this will be evaluated from 0 to pi over 12. Now for this piece, I'm going to go ahead and evaluate. So this would be 5 pi over 12 minus pi over 12. Half of 50 is 25. The integral of 1 d theta is theta minus 1/4 sine of 4 theta. Now this one is evaluated from 5 pi over 12 to pi over 2. Okay. 25 out front. So this is my upper, so this would be pi over 12 minus 1/4 sine of 4 pi over 12. So there's your upper minus my lower. So I'm going to have 0 minus 1/4 sine of 0. I think I need one more set of brackets. Now here I have 25 halves. 5 pi over 12 minus pi over 12 is 4 pi over 12, which reduces to pi over 3. Okay, and then I think on this one I'm going to run out of room. So I'm going to move down here for part 2, plus 25. So I have pi over 2 minus 1/4 sine of 4 pi over 2. 5 pi over 12 minus 1/4 sine of 4 times 5 pi over 12. Close parenthesis, close bracket, close bracket. Okay. So we've got quite a bit going on here. Nice thing is this piece falls away. Let me see about this one. 2 goes into 4 twice. Sine of 2 pi. This falls away, but not this piece. That stays. And then over here, yeah, that piece doesn't fall away, so I'll have to keep track of that as well. So I have 25 pi over 12. I'm going to go ahead and distribute that 25 minus 25 fourths sine pi over 3. So this is going to be square root of 3 over 2. Then over here I have plus 25 pi over 6. It's from right here. And over here I have plus 25 pi over 2. And again, this piece went to 0, so I don't need to worry about that. And let me double check my parentheses here. That was 25 was out front of everything. Yep, so this 25 still comes over to here. So that's minus 25 minus 125 pi over 12. And this one's tricky. A negative times a negative is a positive. 25 fourths. So this would be 5 pi over 3. 5 pi over 3 is in the 4th quadrant. So the sign's negative, so this is going to be a negative square root of 3 over 2. Okay. So we want to keep simplifying. So I have 25 pi over 12 minus 25 root 3 over 8 plus 25 pi over 6 plus 25 pi over 2 minus 125 pi over 12 minus 25 root 3 over 8. Okay, so there's quite a few like terms we can combine. For instance, I have 25 pi over 12, negative 125 pi over 12 is a negative 100 pi over 12. Minus 25 root 3 over 8 minus 25 root 3 is minus 50 root 3 over 8. And these I can combine as well if I multiply top and bottom by 3 for that common denominator. So 25 pi plus 75 pi is 100 pi over 6. Okay, so then I can combine these two. If I multiply top and bottom by 2, so I get that common denominator. So I end up with a negative 100 pi over 12 plus 200 pi over 12 minus 50 root 3 over 8. So 200 pi minus 100 pi is 100 pi over 12 minus 50 root 3 over 8. And I can reduce both of these. So this would be 50 pi over 6 minus 25 root 3 over 4. 50 pi over 6 reduces to 25 pi thirds minus 25 root 3 over 4. So this is the area of region 1. And what we want to do is we want to multiply that by 4. So our total area would be 4 times all this. 25 pi over 3 minus 25 root 3 over 4, which would be 100 pi over 3. I'm going to distribute that 4 minus 100 over 4, which is minus 25 root 3. So my area for all of those regions is 100 pi over 3 minus 25 root 3 units squared, because again it's area. Okay, so some of these can get a little bit long, and most of these was computational. The calculus part of it wasn't too bad at all. Kind of had to remember back to some older integration techniques, but it's very doable. So again, I'll provide graphs if needed to help you find these regions, and of course you'll provide all the arithmetic and integration skills. As usual, if you have questions, please let me know. Enjoy this section. These problems get a little bit long, but stick with them because they are very important, especially when you're going to start preparing for your third semester of calculus when you're using double and triple integration.